Hello again. Let's talk about Chapter 17, Acids and Bases. So, properties of acids. We have the chemical formula and structural representation of acetic acid there in the top right corner, and that's vinegar. So, you probably already have that in your house right now, in your kitchen or in your cabinet, right? Um, Acids have a sour taste to them typically. They may dissolve metals if they are strong enough. They neutralize bases, and they change blue litmus paper to red. That's some identifying features of acids. And then I grabbed this graphic down at the bottom there where we can see some common acids, right? The vinegar I mentioned earlier, we can have citric acid in our citruses and fruits, battery acid in your car, and phosphoric acid in your soda. Acids have a nonmetal attached to a hydrogen. And as long as that hydrogen is very polarized, it's easily taken up by a base, we would have an acid. And so this is just a representation of hydrochloric acid, chlorine being the larger electronegative element, larger electron cloud is that green one, and the white, as we've seen in previous models, is our hydrogen. We have a subcategory of acids called oxyacids, and so this is just a type of chemical where hydrogen is specifically tied to an oxygen. And so you can see sulfuric acid there on the left, which is H2SO4. And so we have a model representation, space filling model here, and then we have a skeletal formula as well. And so these two hydrogens are coming off of oxygen atoms. The other two would not be able to have a hydrogen on them because they're being double bonded to the sulfur. So all of their bonds are being taken up. But these two oxygens are each bonded to the sulfur once, and so they have another bond location open for each of those hydrogens. So this is what we call a diprotic because it's got two hydrogens. We'll see a little bit more of that later. Nitric acid over here on the right just has one little hydrogen, but it's attached to an oxygen as well. So these would both be classified as oxyacids. Carboxylic acids, you may remember from biology class. And so, of course, they're an acid, so we can talk about them in a chemist point of view. Just slide myself down here so you can see the rest of the formula. Oh, we're cut off anyway. That's good. Right at the cut there. So a carboxylic acid is C double bond O OH, and biologists tend to write it this way that you see here with the O's right next to each other. Chemists will place it in their formulas like this. So you could see it either way. You should be able to recognize it either way. And this key point here is something to point out. Only the first H in the formula is acidic. The H that's on the C double bond O. Okay, if you look back at these formulas for acetic acid, our vinegar, and then our citric acid over here, there's several hydrogens. And see how they're being separated in the formulas as well? So usually the way formulas are written, they're written left to right in the order that you would write the skeletal structure, like this top picture up here on the right, for those molecules. So I would write 3 hydrogens, and they would connect to 1 carbon, then a few chains of carbons with a couple hydrogens branching off of each, and then I would have this typical ending, since I know it's a carboxylic acid. I would have a C double bonded to an O, then an O and an H, because I know that it's that class of acid. Not too critical here, but if you're planning on taking organic chemistry in the fall, you'll get to draw a lot more of those. Okay, bases. So sometimes bases are called the chemical opposite to acids, and that's not exactly true. They do neutralize one another, and maybe that's where that came from, but they are their own substances with their own properties, their own strengths and weaknesses. So with bases, we can have some plants. This is a nightingale plant here that's poisonous for humans. So I put that here because of this point that the book wants to make. Plant products, alkaline, okay, alkaloids, are the name of those products. Alkaline is a general term meaning basic. If you have any device that still runs on batteries, if you take a look at them, AA, AAA batteries, it'll say alkaline on them, and it's has to do with the chemistry that involves the battery. So you've seen this word before. Bases typically have a slippery feel to them, so when we were working with NaOH in the lab a couple times so far this year, if you've gotten any on your skin, you may have noticed it felt really slippery. That's because NaOH is a base. Ability to turn red litmus paper blue. Remember, with the acids, we had blue paper that would turn red. So if it's red, you're not going to see red on it because the paper's already red, right? So you have to use the opposite paper when you're testing. And so another way to remember this is that bases turn blue. So blue base, right? They both start with B. That's like a little way that you can remember one versus the other. So I have a similar graphic that I had for the acids where I picked some everyday common materials. So ammonia is NH3. That's a typical cleaner. It has a very strong odor to it if you've been around that or used it. Borax is not really used much anymore. It's a detergent chemical. It's usually sold in a box on its own, not in a detergent. You'll see it's usually the bottom shelf because it's not really a popular item anymore, but you could do some fun crafts with it. And then we have a bar of soap, and baking soda as well is also classified as a base. So we're going to have three different schools of thought here, and they arise from these gentlemen here who have done their research and looked at acids as their different chemistries. And so the first one we're going to talk about is Arrhenius, and that's him there in the top picture. He would say that an acid produces hydrogen ions in a solution, and the hydrogen ions always connect with water that's in the solution and form the H3O plus, or the hydronium ion. He also said that bases were chemicals that produced a hydroxyl group in solution, so an OH. Whereas Bronsted-Lowry, the two gentlemen you see on the bottom, they looked at acids and bases as what they're doing with protons exclusively. So they would say an acid is a proton donor because it would give up a hydrogen off its molecule, whereas a base would be a proton acceptor, taking in that hydrogen for that acid-base reaction. So if we focus back on the Arrhenius definition here, we have a picture. A substance that produces hydrogen ions in an aqueous solution. So we have a reaction here. We're told we have hydrochloric acid, and it's in an aqueous solution, so water is there. We don't need to write it. And the chemistry is HCl will split apart into a proton, which is that hydrogen ion, and a chloride molecule ion. And so we can look at the graphic here and just see how they are just split apart as ions in that solution. And that's the definition for Arrhenius. Anything that produces an H plus is an acid. So let's talk about this hydronium a little more. So when we have an aqueous solution and we have an acid that's losing protons, these are readily taken up by water. Water's got that oxygen on it with the two lone electron pairs, and so just a lonely old proton would just be snatched up very quickly by that oxygen and its lone electrons. So hydrogen ions, it says, are very reactive. They can't exist in the water. They are just a proton. And I have that on a different slide here. We'll see a picture to help you kind of visualize what I mean and how I can interchangeably say hydrogen ion and proton. They are the same thing. So hang on, we'll stay tuned for that. But when they do react, and we have this H3O plus, that's called hydronium. And you may remember that from Chem 1 when you had to learn all the polyatomic ions. It's one of two that are positive polyatomic ions, the other being ammonium, the NH4 plus. Okay, so we see a reaction written here as a water molecule kind of gobbles up that lone hydrogen in solution. And so it says there are also minor amounts of H plus with multiple water molecules, And so they can write this kind of general formula with N being any number of waters that would attach, but that's not how it's usually discussed in a class like our level, so we would just stick to the H3O plus. All right, so the Arrhenius definition of bases is something that produces OH ions when it's in an aqueous solution. So we've got some sodium hydroxide. We're going to dump it in this beaker of water, and we see that it just splits into those two ions, sodium ions and the hydroxide ions in the solution. So we can have an Arrhenius acid-base reaction where we have the acid that produces the H+, that H+, then combines with the OH ion from the base, and it makes a molecule of water. Take a look at this. We have hydrochloric acid here. This is an acid. It has a hydrogen, and it's bound to a very large electronegative anion. So this is very polar. You could argue ionic, but it is kind of polar. That's a whole nother discussion. But this hydrogen would easily come off of that chlorine. And take a look at our sodium hydroxide here. If I take this OH out and combine it with the proton from hydrochloric acid, I've made H2O, haven't I? H, H2, and then an O. And so here it is. And so we have the water made from both of these components reacting. And then whatever's left, we had a sodium ion and a chloride ion. Well, they're oppositely charged, so they would gravitate towards each other. You know, kidding aside, right? No gravity involved, but and we have our sodium chloride. So here's what I'm talking about with a proton and how we can talk about hydrogen as a proton. So when hydrogen is lost off a molecule, the electron stays behind, right? We looked at the chloride, it kept that electron. It had one pair of electrons there. So where did it come from? It kept hydrogen's electron. And so if hydrogen is defined as one proton, one electron, if it leaves the electron behind with the anion, it's now just a proton. And so that's why we can call a hydrogen ion a proton. And so these are interchangeably used in chemistry, so just be careful. They are talking about the same thing. So just be up with that terminology. So then we can flip over to Bronsted-Lowry. And so they're talking about donors and acceptors. And you might be saying, well, that's the same thing that you just said with Arrhenius. It is and it isn't. So with this, it'll exclude some some compounds, or accept ones that Arrhenius won't quite count for his definition. And so we could take a look at this, right? So a base structure must contain an atom with an unshared pair of electrons. That wasn't part of the definition for Arrhenius. And we have here a hydrogen associated here with a positive A molecule. We have a B for our base, where we see a lone pair there, that double dot. And so what happens? Now the H goes with the B, and then the A is left as an anion with a lone pair. The general equations are not always the best to look at this. Let's take a look at a real example. Okay, so again, Bronsted-Lowry acids are proton donors. Any material that has a hydrogen could potentially be a Bronsted-Lowry acid. One of the hydrogens in the molecule would be easier to transfer than others. So far that matches Arrhenius, right? And so if we look at hydrochloric acid in water, water's pretty special and unique, and we'll see that also in this chapter. So right now, let's say we have hydrochloric acid and we dump it in some water, pure water. See how it's in the liquid state there? It's not aqueous solution already with something else. So we have pure water, deionized water. And what happens here, if we follow the reaction from reactants to products, the hydrogen came off the hydrochloric acid, attached to the oxygen of water, and we got a hydronium ion. Right? That's just what we saw with the Arrhenius definition too, right? But here we're using water. We're not using NaOH like Arrhenius did. There's no OH forming here for Bronsted-Lowry, right? Water didn't release an OH into solution. It stayed H2O and picked up that hydrogen from hydrochloric acid. So that's where the definitions are different. Let's take a look at the Bronsted-Lowry base definition. So the base definition is, again, nothing to do with OH like Arrhenius is. It's just a chemical that will accept a proton from someone else. And so a typical example here is ammonia, NH3. If we drew the Lewis structure out for ammonia, we would see a lone pair of electrons up on top of that nitrogen. And so that was the criteria that was mentioned in the first slide for Bronsted-Lowry, that it had to have that lone pair on the molecule. That's what's going to grab the hydrogen from whatever the acid is in solution. Now take a look at the reaction at the bottom here. See water again, but it's got a different label under it. It says it's an acid now. What? So you're not imagining things. We go back. Yep, there's water at the bottom and it says base. And here's water at the bottom on this slide and it says acid. So water is unique in that it can behave as an acid or a base. So more on that in a minute. So it's in here with ammonia, which is definitely a base. So water will play the role of an acid and it'll give up one of those hydrogens. And so now we see just an OH in solution. And we have our ammonium ion that formed. So yeah, hydroxide did form in this process, but it was secondary to the overall chemistry here. So it's still not quite Arrhenius, okay? All right, so here we go, amphoterism. So amphoteric means that it could be an acid or a base. Like if someone can write with both hands, we call them ambidextrous. And so this is amphoteric. I don't know if that helps or not, but it's some similarities that you may have associated them together. And so we can just summarize both of the reactions we've just seen and just follow water from the reactant side over to the product side. Look at it as it's on the reactant side, okay, it's H2O, and then find the similar looking molecule on the product side, and then you'll see what happened to that water. And so on the top, we could see it went from water to hydronium, picked up a hydrogen. Might be a little harder to see here because water really loses its identity when we get rid of one of those hydrogens. So in this reaction, we just see the OH, but that was from the water. Okay, it couldn't have come from anywhere else. So that's where water is acting as an acid in that case. All right, so let's talk about Bronsted-Lowry acid-base reactions. So it says one of the advantages of the Bronsted-Lowry theory is that it illustrates reversible reactions. And again, we see a general form here. The original base has an extra H after the reaction, so it can act as an acid in the reverse process. So we did not see this with Arrhenius. Arrhenius was a one-way reaction, but if we follow the Bronsted-Lowry definition, where a base just needed that lone pair, there could be another hydrogen that could then now be acting as an acid, donating, and we can get a reversal of the reactions. So, let's take a look at real molecules here instead of those general equations. It's kind of tricky with this topic, right? So here we have two different ones. Let's just read the bullet points up top here first, and then we'll look at the pictures individually here. So it says a Bronsted-Lowry acid-base reaction. The original base becomes an acid when the reaction goes in the reverse direction. So we can say that again as the original base becomes an acid as a product. So it's a base as a reactant and then an acid as a product. And then we can flip that statement. The original acid in the reaction will become a base for the product side. And so it's just that proton losing and gaining. Let's take a look at the two reactions down here at the bottom. and what we determine to be a conjugate pair. So if we look at ammonia, which is just NH3, we know that that's a base now because of its lone pair. And so we're going to get used to seeing ammonia used a lot, and you're going to get to know ammonia is a base, just like that. So if we add a proton, it becomes NH4. Now, if we look at NH4, do you see how it could donate that proton back, which would be an acid behavior? And so that's why these reactions are reversible. Now let's take a look at water behaving as an acid in this case. It's going to get a hydrogen removed from it. That's the definition of an acid. And it is now a conjugate base. It could accept another hydrogen. And so that's why with Bronsted-Lowry, we can have reversible reactions. Okay, so when we're looking at a reaction and we're trying to follow what happens from the reactant side to the product side, with Bronsted-Lowry, we would tag those related chemicals as conjugates. And so you can see how the bases are in blue, that's on purpose, and the acids are in red text because of how they change litmus paper. They change blue paper red. So that's a typical format that you see for acids and bases, kind of help your mind if you're visual. And so the base, we'll talk about that first since it's to the left. So the base, ammonium, follow the blue, it becomes a conjugate acid. So the base has a conjugate to it, which is an acid. The acid, which is water in this reaction, follow the red line, becomes a conjugate base on the product side. So acids have a conjugate base. Bases have a conjugate acid. And it's just following that proton from reactant to product. Okay, here's our first example. So you should have your note sheet printed out. Here we go. In each reaction, we've got two parts here. Identify the Bronsted-Lowry acids. You could just say acid. You could write it underneath or above the formula. And the Bronsted-Lowry base. You could just say the word base. And then what we typically do is we would abbreviate conjugate acid as just uppercase C, uppercase A, and conjugate base, uppercase C, uppercase B. So you want to, again, follow the proton and determine how each substance is behaving. You can go ahead and pause the video for a second, try it out, and then we'll go over it. All right, so here we are. So for A, because H2SO4, which is sulfuric acid, donates a proton to the water in this reaction, it's the acid. After H2SO4 donates that proton, we could follow it up here, it becomes HSO4 negative. So now that's a conjugate base. Because it's a negative, it could accept a proton, which is the definition of a base. So we have that labeled down here. Water has to be acting as a base in this reaction, and so it became a hydronium, which is an acid, because that H, that third hydrogen, can be now donated back to the conjugate base, and then we would get our original products back. How'd you do? How about B? So B, we have carbonic acid here, and so we have it acting as a base on this side. So it's going to accept a proton from our water that's behaving as an acid in this reaction, and it becomes carbonic acid here. So that's its conjugate acid. And then the water that remains is the conjugate base. And so you should be able to look at these two on the product side, and see that one of those hydrogens can be given back to form water. Here it is. And then what would be left? We would just have one H and a CO3. But don't forget that negative sign, because the hydrogen is a proton, so it's taking its positive charge with it. Over here, the H2CO3 is neutral. Okay, look at your polyatomic ion sheet if you still have it. CO3 is a polyatomic ion with a -2 charge. So the two protons are equaling that out. So if we lose one, we're going to have a negative remaining. All right, strength. So strong acid is a strong electrolyte, and so electrolytes just will carry an electric charge through solution and move electrons through solution. So we say practically all the acid molecules ionize or break apart to form ions. A strong base is a strong electrolyte as well. Look at that negative charge it has. Practically all the base molecules form OH ions. Practically, remember, ammonia does not, either through dissociation or reaction with water. And so ammonia would be through the reaction with water option. A weak acid is a weak electrolyte, which says that only a small percentage will ionize. A weak base is a weak electrolyte. Only a small percentage of base molecules form OH ions. And so I'm not quite sure what happened with this symbolism here. I'm not sure what that is, but we'll explain the chemistry right here. So if it's a strong acid, that just means it completely breaks apart into its ions when in water. It's strong if it all breaks apart. Okay, the brackets here represent concentration, so molarity. So you're going to see that a lot. So the concentration of hydronium is equal to a strong acid concentration. So HCl would be a strong acid because when it's in water, this should say dissociate, not dissolve, because it's still there, right? So it breaks apart into hydrogen and chlorine. And so we have the hydronium ions grabbing those hydrogens, and then the chlorines are just kind of stuck there, right? So because the H and the Cl completely separated, there is no remaining HCl stuck together still in the water. That's 100% ionizing, so that means HCl is a strong acid. A weak acid is something that doesn't 100% become ions. So it says here, much less than 1%. That's not much at all, right? Most of the molecule is remaining intact when it's in water. And so here we see hydrofluoric acid. And so this is when the hydronium ions are in a very low concentration. And that's because only a few hydrogens are coming off from the fluorines. And so there's only a few hydrogens to bond to water that's in the solution. So that's our hydronium ion, and we're not registering much on a pH meter. And so most of that molecule is remaining intact. We could see a bunch of hydrofluoric acid molecules staying together. That's what defines a weak acid. All right, so the strength. The strength of the acid depends on the degree of attraction of the acid anion and the H plus ion. Okay, so like the conjugate base of the acid. Commonly, acid-base strength is measured by determining the equilibrium constant of a substance reaction with water. The smaller the ionization constant, which is also K, like we had equilibrium constant in the previous chapter, when we're referring to acids and bases, the K stands for ionization constant. So the smaller that value is, the weaker the acid or the base is. The position of equilibrium is going to depend on the strength of attraction between that base form and the H+. If it has a stronger attraction, it's going to be a stronger base because it's grabbing that H, or it could be a weaker acid. We'll see examples of both of these. Okay, so again, a picture, visual learners. Strong acids are when we have a weak attraction and that hydrogen is easily pulled off of the anion, and we call that complete ionization. They've all become ions. A weak acid at the bottom has a stronger attraction, so the hydrogen is not easily pulled away from the anion. And so only part of the molecule is ionized. Some remain intact as an acid. And so that's a weak acid. So it might be confusing where you see strong and weak together in the same definitions, but I think this picture is helpful in seeing that a strong acid completely breaks apart and a weak acid, not all of it completely breaks apart. Okay, let's just see more examples. All right, so here's the K value for acids. So we have a little subletter A next to the K when we're talking about acids. So the acid ionization constant is the K sub A together. Acid strength is measured by the size of the equilibrium constant when it reacts with water. And so we see our reaction there with water acting as a base. Okay. The equilibrium constant for this reaction is called the acid ionization constant, or Ka. The larger the Ka value is, the stronger the acid is. And so based on the reaction that we see up at the top of the screen there, or kind of in the middle, we can write the general form of Ka a couple different ways. So we could say that it's the conjugate acid concentration and the anion concentration, right? So still products on top, over the original acid, which is our reactant here. Remember, in equilibrium, same as last chapter, pure water is a liquid, and so liquids and solids are not included in equilibrium equations. So that's why it's not here. And then we can also rewrite this, instead of saying hydronium, to just the proton. And so that's the difference between these two equations. All right, I'm going to move my screen down just a bit so I don't cut off that reaction there. Okay, so we said that water is amphoteric, which means it can act as an acid or a base. So there's going to be a few ions with that. When water acts with itself, we can have water-to-water reactions. How's it going to know? Well, do I play the acid in this reaction, or am I playing the base? It's just completely random. Just however the water molecules interact with each other. We can go talk about collision theory and orientation and energy behind the collisions. That's what's going to drive it. So it's just completely random molecule to molecule. But we would call that auto-ionization. It's ionizing on its own. There's no other chemical there driving that force. And so any sample of water, if you have a water bottle nearby, is doing this all the time. But it's so random that it's never too acidic or too basic that you can even taste it. Think of how many millions and trillions and billions of water molecules would be in that water bottle. So it's just not detectable. But this is an equilibrium that's happening all the time. And so we can say that all aqueous solutions contain both an H3O, that should be together to make more sense, right? And an OH. So we could say that the concentration of the H3O plus, here I am down here, and the OH are going to be equal when we're in water. For every water reaction, I'm going to have a hydronium produced and a hydroxide ion produced. So they're going to be equal all the time. So then we could say that the concentration of hydronium is equal to the concentration of hydroxide. And this is 10 to the negative 7 concentration when we're at room temperature. Okay, that negative 7 exponent is going to be significant in just a minute. So then we can have something called the ion product of water, and this is represented by K sub W for water. So when we have the product, we're multiplying the concentrations, like you just saw on the previous slide, hydronium and hydroxide, you're always going to get the same number. That number is the ion product. It's also known as the dissociation constant, since this is breaking apart, which is called dissociation. And so we can say that the H3O plus, when it's multiplied by its counterpart hydroxide concentration, that's going to be equal to this ion product, Kw. And Kw is equal to 1 times 10 to the negative 14. What did we have on the previous slide? We had 7. That was for one of them. Here's the other 7. Now we have 14 when we look at both together. And that is still at room temperature. If you measure one of the concentrations, you can calculate the other because they add up to 14 for that exponent. So as the hydronium ion concentration increases, the OH must decrease so that this product remains this value here, 1 times 10 to the negative 14. So we could say that that's inversely proportional, meaning as one concentration increases, the other will decrease. Those are inverses. Okay, all aqueous solutions will contain both hydronium and hydroxide because of that autoionization of water. So if water's there, it's doing this. And so neutral solutions will have an equal amount of each. So the concentrations will each be 1 times 10 to the negative 7. Acidic solutions are classified as such because they have a greater concentration. So we have a greater than sign here, just meaning that the hydronium concentration would be greater than 1 times 10 to the negative 7. And it could be just by a couple decimal places or 1 decimal place, as long as it's greater than the 1.00 times 10 to the negative 7. And then the OH would have to be less than, because again, it has to add up to 1 times 10 to the negative 14. And then basic solutions are classified where the hydroxide ion is greater than 1.00 times 10 to the negative 7. And so in that case, the hydronium ion must be less than that value. Here's our second example. Calculate the hydroxide ion concentration for each solution and determine if the solution is going to be acidic, basic, or neutral. So let me give you some guidance, and then you can pause the video and try it out. For all three of these examples, we're just told the hydronium ion concentration. We need this to add up to 10 to the negative 14. That would be hydronium and hydroxide together. Give it some thought, and we'll go over it in a second. Okay, let's talk about A. So for A, we're going to use Kw, okay? And we're going to use the fact that when we multiply the two concentrations together, we get 1 times 10 to the negative 14. And so in this case, for A, we're given the hydronium ion concentration, so we're going to plug it in that spot. And then we have the other side of the equation, the 1 times 10 to the negative 14, and so OH becomes our variable. And so we would algebraically just solve the equation, and we get 1.3 times 10 to the negative 10. That's the OH concentration. Remember, that's what you calculated, the OH concentration. Okay? So we can then compare this, the 1.3 times 10 to the negative 10, to our original hydronium ion concentration, which is 7.5 times 10 to the negative 5. The hydronium ion concentration is greater than the hydroxide we just calculated. So this is an acidic solution. Let's look at B. Okay, same thing. We were given hydronium ion concentration again, so we're going to plug it into that equation, set it equal to 1 times 10 to the negative 14, algebraically solve it, and in this case, we get the hydroxide concentration as 6.7 times 10 to the negative 6. Is that what you got? Okay, we then are not done, right? So algebra kind of trains your mind to think, I got the equals, so I'm done. But we're not done with this problem because we have to compare it to the hydronium and see which concentration is greater to make that decision. And in this case, we have times 10 to the negative 9 compared to times 10 to the negative 6. 10 to the negative 6 is a greater number, and so that's with the hydroxide. This is a basic solution. And lastly, for part C, we're going to, again, plug it in, and what we see is we get the same value for each concentration. So guess what? That's neutral, plain old water. All right, so now you've seen how we determine the pH, really, is what we were finding out, the concentration of hydrogen ions, or hydronium. And we often express this as pH. It stands for partial hydrogen, or sometimes you'll see derivations of that phrasing to like a Latin version. But basically, it's part hydrogen. What part is hydrogen? pH. And so the calculation to figure out this is when we take the negative log of the hydronium, hydronium ions. So, because we don't mention pH as 10 to the negative 7, right? This is almost done for, the general population to be able to talk about pH, because this is such a confusing subject. So if we can just get rid of that times 10 and the negative part, which is what this negative log does, it becomes just a flat number that is easier to communicate. So that's pH. So we need to know the hydronium ion concentration to figure out pH. That's how it's connected. And so when we determine this by plugging in the formula for any concentration that's given, if we end up with a number less than 7, that's considered acidic. If it's greater than 7, it's basic. And if it's right on, equal to 7, it is a neutral concentration. So we can say that the hydronium ion concentration is equal to 10 to the negative pH. Because look what happened up in the equation above. Negative of the pH, our pH was found to be 7. So if we're given 10 to a negative value power, that power is the pH. Okay? It's a little different for hydroxide, but we still know the Kw, they've got to add up to times 10 to the negative 14. Okay. So the pH number. So the lower the pH, the more acidic. The higher the pH, the more basic. 1 pH unit is a factor of 10 difference in acidity. So it's a logarithmic scale. We just saw log in the equation on the previous slide. So the concentration jumps incrementally that way. So we can say that the normal range of pH is 0 to 14. Some charts say 1 to 14. I think it's more accepted lately that 0 is in there. So 0 is like super acidic. So a pH of 0, the hydronium ions equal 1 molar. And the pH 14 is when the OH concentration is 1 molar. pH can be negative, which is very acidic. Okay, that's very, very rare. Or larger than 14, and that's like super alkaline, which is also very, very rare. Only decimal places are significant figures in pH values. So when we looked at significant figures earlier in the semester, we saw that the zeros were only significant if there was a decimal present. And so here we are, right? That's why we're expressing the pH with these number of decimal places, because when we calculated it with the log, we had 2 sig figs here. Okay, example number 3. So calculate the pH of each solution, room temperature, and indicate whether the solution is going to be acidic or basic. So using the log equation, try out A and B. Okay, so part A, the first question, we have to substitute the hydronium ion concentration into the pH equation. And so we have pH minus log concentration of hydronium. And so we plug in the 1.8 times 10 to the negative 4 for that hydronium. We plug in the calculator very carefully, the negative log of this value, and we get negative 3.74. So the negatives will cancel out. Our pH is 3.74, which is less than 7, so this is acidic. B is a little trickier. You've got to be careful what you're given. We are given a hydroxide ion concentration. This cannot directly plug in to the log equation for pH. That's OH that was given. So we first have to figure out what hydronium concentration we have given this hydroxide ion concentration. So we have to use Kw. And so using Kw and the given hydroxide concentration, we end up with our hydronium, boy, it's getting tricky, equal to 7.7 times 10 to the negative 13. We're not done. We've got to plug that in now to the pH equation, because we just found the hydronium concentration with Kw. We now are not done. We need to plug it in to the pH equation to get the pH. And when we do that, it simplifies to 12.11, which is greater than 7. So this is a basic solution. We're jumping right into example 4. Take a look at this. Calculate the hydronium ion concentration for a solution with a pH given of 4.80. Sounds like we're going backwards in the math from what we've been doing. Try it out. Okay, let's walk through this one. So, start with the equation that defines pH. We're going to substitute the given value of pH and then solve for the hydronium ion concentration. And so remember mathematically that the backwards version of taking the log is this value here, 10 to the log x power. So take a look at your calculator that you're using. You might have a button that says inverse log, and then you would use that. So it's going to depend on your specific model of calculator. So you need to know which way you need to go to do this type of problem. And so here we go. We're plugging in the pH. We were given that. And so we're going to algebraically manipulate this equation around, and this is what we get. 10 to the negative 4.80 power. Remember, that was related to the pH a few slides back. And then that's going to be equal to 10 log of the hydronium ion concentration. It's kind of hard to type that, so that's why it looks funny. And so then we could simplify the right side further and just say that 10 to the negative 4.80 is equal to the hydronium. So we would plug in this left value of the equation into the calculator, and that spits out 1.6 times 10 to the negative 5. So that's our hydronium ion concentration. Okay, so half of the story that's not talked about nearly as often as pH is pOH. And it's just what you think it is. It's how we express the acidity or the basicity by looking at the OH concentration, so partial OH, right? pOH. And so it's calculated the same way as pH, but just remember you're using the hydroxide concentration, not the hydronium. And so we're using negative log again. We need to be given the hydroxide ion concentration or figure it out with Kw. And the pH plus the pOH has to come out to 14. We did say that sometimes we have a value less than 0 or greater than 14, but for the most part, we're sticking in that range. So we're going to go ahead and make this statement that pH plus pOH is going to equal 14 even. Okay, so here's how they relate to each other. So pH plus pOH is 14. Again, this is room temperature. You can use the pOH to find the pH, right? So you need to know all these relationships, okay? The 14 is very significant because then that's our Kw, right? And so this is going from Kw to the statement that we just learned, the pH plus pOH. So all this is a bunch of scary looking math to just get us to that equation. All right, pK. This is another way of expressing the strength of an acid or a base. The pKa is the negative log of the Ka. Remember that was the equilibrium constant, our ionization constant for an acid. And then here's the base counterpart. It just has a sub B there. And so we can have the pKb, or pKa, is equal to negative log of that partial equilibrium value. And then we have the Ka and Kb equal to 10 times those powers. Here's the thing. It's an inverse relationship. The stronger the acid is, the smaller the pKa value is going to be. And that's because we're taking the negative log of that. Okay, you don't have to know why, but just know this relationship because you're going to be calculating pKa and then be asked, which one's stronger? Maybe you're calculating a couple and you're then going to compare, or is this strong or weak just looking at one? You're going to need to know this relationship. Okay, there are two sources of hydronium in an aqueous solution of a strong acid, the acid itself and the water. For a strong acid, the contribution to the water to the total hydronium is like really nothing. The hydronium from the acid is what's going to shift the Kw so far to the right that the hydronium coming from water is so small it's not going to matter any. So the way we narrow that down then is we could say that the concentration of hydronium from the acid is directly equal to the concentration of the acid. All right. There's also two sources of hydronium in an aqueous solution with the weak acid. Again, the acid and the water. But finding the hydronium is complicated because the acid only breaks apart partially. That's what a weak acid is. It's not completely dissociating like a strong acid does. So it becomes a little more intensive. So calculating the hydronium means we have to make it an equilibrium problem and work it that way because of that partial ionization. It doesn't completely ionize, so it has to be an equilibrium problem. So here's our steps, and then we're going to try an example. So to find the pH of a weak acid, we're going to write the equation, and we're going to write an ice table, just like we did in the equilibrium chapter. We're going to plug in what's given, and keep in mind the stoichiometry for that C change line. We're going to substitute the expressions for equilibrium into the Ka expression. We're doing acid here. We'll determine the hydronium ion concentration from the calculated value of X, and then from there we can get the pH. So here we're going to show all of those steps in a specific problem. So this problem is example 5, and it says, find the hydronium concentration of a 0.100 molar cyanide acid solution. Okay, so first we're going to write the balanced equation. We're dumping it in some water, which is a pure liquid, and then look what's going to happen. We're told this is an acid, and so that proton is going to go to the water. Here it is, H3O. What's left after that proton leaves here? Just the CN, the cyanide anion. So we write that. It's an equilibrium because this doesn't completely break apart. Some of it remains in solution. And so our initial is 0.1, that was given. Our hydronium is virtually nothing because of that weak, very few of those acid molecules breaking apart to make hydronium. So we could say it's 0, and the cyanide 0. Okay, change is done the same way as last chapter with just an X for right now as a placeholder. So we know that we're losing a concentration of our acid on the reactant side, and then we're gaining some value of hydronium and cyanide on the product side. There are no coefficients here in this reaction, so they're all just X. Then we're going to total them down to get the equilibrium expression numbers that we need. And so here's what we get highlighted in red. Okay, next is to plug that into the K expression. Remember, it's products over reactants. That didn't change, but we just call this Ka for the weak acid. Okay, 0.100 is such a small number that if I subtract whatever X equals from it, it's probably not going to change the fact that it's just really small. So when you have a situation like this, 0.1 minus X, we can do what we did in the last chapter and say neglect X with regard to 0.1. That means wherever X is next to a 0.1, we're going to just take it out. So that simplifies the algebra a lot. So here we have just 0.1 now. The minus X has been neglected, it's out. That leaves us with just X squared. We're going to square root both sides. We're going to simplify, and we're going to get 7.0 times 10 to the negative 6. Well, to check that it was okay that we said neglect X to make sure that this wasn't a significant subtraction, we can then throw it over that original concentration, multiply it by 100, and if it's less than 5, we're okay. Here we're at 10 to the negative 3, which is really less than 5, so we're okay. It was okay to take the X out. All right, we're not done. Determine the hydronium from the calculated value of X. So we just found that the hydronium concentration was the 7.0 times 10 to the negative 6. That last step on the previous slide was just a check that it was okay for us to neglect X. You don't really have to do that step, but it's a little insurance. So really, we stopped where we solved for X, and that was our hydroxide concentration. pH was not asked for in this problem. We could figure that out at this step if it were. And so now, we're going to check by substituting the calculated equilibrium values into the Ka, right? We have our products over reactants. We found our hydronium. Here it is. We know that the hydronium and the cyanide were a 1-to-1 ratio because of the balanced equation. So this would essentially be squared. And we were told in the problem what our concentration of the HCN acid was. So we put that in the bottom. And when we simplify, we get 4.9 times 10 to the negative 10. Since this Ka matches the given value, we figured it out correctly. Again, step 6 is a check. It's not necessary to do for every problem. So if you'd like to try it, this is how you would do it. All right. Example 6. Step 1 is already placed up there, but go ahead and pause the video and try it the way we did example 5. And then come back here with the video and see how you did. Okay, so here we are at example 6. The pH of a 0.2 molar nitric acid, nitric acid, NO2, solution. And so this is a weak acid. And so now we have our equation. Because it's a weak acid, we have to write it as equilibrium, which means ice table. We were given the initial concentration of our acid as 0.2. The hydronium is basically 0, and the nitrite is 0. The change, again, this is all coefficients of 1 in this balanced equation, so it's just going to be minus x for the reactant and plus x for the products. We're going to carry that down to the equilibrium line, and now we have what we need to plug into Ka. So here's our Ka expression, okay, products over reactants, and we see a similar scenario that we saw in example 5. 0.1 and 0.2 are very similar, they're small. So let's go ahead and try this again where we could say neglect x when it's next to 0.2. That way we simplify the algebra, we avoid the quadratic equation. So we can come down here and square root both sides, we can simplify, take the final square root, and what we get is 9.6 times 10 to the negative 3 for our Ka. The last division and then multiply, this is our check to see if it was okay. You don't have to do this step. This is the check to see if neglecting x was okay to do. Here we get 4.8, which is just a hair under 5, which is our cutoff. And so this will still be okay to continue, but maybe a good idea to just maybe check if it's a little higher than 0.2, right? Maybe we're not as comfortable as we thought. So we continue on, and we can get the hydronium concentration from what we just calculated, which was our x, by plugging it into the log for getting pH. And so we plug this value in. That 3 up there, don't get confused, that's from the H3O, okay? Our number was 9.6 times 10 to the negative 3. So taking the antilog of that gives me 2.02. We could then check again, like you saw in example 5. We don't have to do that step. We figured out the pH was 2. So it's somewhat still strong, but it's a weak concentration for it. So here's how you would do the check for example 6. Okay, let's look at 7. We're doing them all in a row now. A 1.00 weak acid, we're told just generic HA, has a pH of 4.25. Find the Ka for the acid. Okay, this is different. But again, it's the same steps. We're just going to change the order a bit. We were given pH. We didn't have to solve for it. So we're going to work backwards. We have the pH is equal to the antilog of hydronium. We're given pH, so let's plug it in. And that's the antilog of hydronium. If we do our algebra, we would get the hydronium concentration equal to 5.6 times 10 to the negative 5. That's at equilibrium. So we can plug it in on the hydronium column for equilibrium. See how it's down here? This is again for a problem that we're given the concentration initially, we're given the pH, and we're asked to find Ka. So that's the only scenario where we can plug this in down here. Let's go on. We're going to use the equilibrium concentration of hydronium and the stoichiometry of the reaction to predict the changes for all of the species. So we're not just going to have minus X and plus X along that change line in our ice table. We know that hydronium concentration is 5.6 times 10 to the negative 5. So the hydronium, let's go up this table here, up this column. It was 0, so that means the hydronium change was a positive 5.6 times 10 to the negative 5. We know that on the product side, our anion here that came from our original acid was also at 0, and it has a coefficient of 1, just like our hydronium does. So it's going to change the same way. So we have a positive 5.6 times 10 to the negative 5 here as well. The original acid, our reactant, started out at a 0.1. The change was it's going to lose by a factor of 5.6 times 10 to the negative 5. So it's not just X. We know more information in this example. So we could simplify that by taking 0.1 and subtracting that value. And we still get like 0.1. It's not much. Subtracting 5.6 times 10 to the negative 5, write that out with the decimals. It's already a very small number. So taking that from 0.1, you're changing decimal places way down the line. It's not going to change the number value that much. So now we can plug this all into Ka. We write our products over reactants. We plug in our equilibrium values, and we get 3.1 times 10 to the negative 8. Hey, that's what they wanted, so we're done. All right, we're almost done with our topics here for acid-base, and so let's talk about the percent ionization. Another way to measure the strength of an acid is to determine the percentage of acid molecules that ionize when it's dissolved in water. That's called the percent ionization. So whenever I look at percents, I relate it to grades because, I'm around grades all the time. So just as you guys, knowing that an 80% is almost all and 100% is all, it's going to be looked at the same way. If it's 100% for our ionization, that's a strong acid because it's 100% breaking apart. Whereas if it's a low percentage, it's going to be a weak acid because only a few of them are breaking apart, the low percentage. So maybe that'll help you in keeping track of what percent ionization really is and what you're calculating when you do that. Okay, when I increase the starting concentration of an acid, you're going to get more hydronium at equilibrium. You just gave it more hydrogen ions to give up. Increasing the initial concentration of an acid will result in a decreased percent ionization. This means that the increase in hydronium is slower than the increase in the acid concentration. It's kind of wacky. But let's look at the equation down here. So the percent is the concentration of the acid over the initial concentration of the acid. Whenever we get percents, it's always taking part over the total and multiplying by 100. Like, you got 5 out of 10 problems correct, so I would take 5, divide it by 10, and then times it by 100 to make it 50%, which is a more recognizable number than 5. And so that's what we're doing here. We're taking part, the concentration of it just being ionized, over the concentration that we started with when it was all together, and then getting a percent that way. Okay, so the hydronium at equilibrium for a weak acid is going to go up with increasing the original acid concentration. The percent ionization of a weak acid decreases as we increase that initial concentration. This is a lot to kind of unravel. As long as you can understand the equations and what I just mentioned with grades and how to calculate the percentage, you'll be fine. So let's go to example 8. This is our second to last example, so we're almost done. Find the percent ionization of a 2.5 molar HNO2 solution. Okay, we're going to make an ice table because to get percent ionization, we need to find the equilibrium. So that's an automatic. We're going to write an equation with HNO2 reacting with water and producing our ions. We're going to write ice, and we're told the starting concentration here is 2.5. Remember, the hydronium ion is virtually 0, so just put 0. You don't need the wavy equal sign. And then our anion that's formed is 0. Okay, here we're not given any other information, so we've got to use X as a placeholder for the change line. We carry it down, we throw it into our Ka value. This should all be, easy steps now. We've done so many. So we simplify. The two x's from the equilibrium are now on the top. It becomes x squared. 2.5 minus x, that's a bit of a risk to say the x would still be small in that case because we have a number that's greater than 1 here, whereas before we saw it was less than 1. So let's go ahead and try it. Okay, so we simplify and we get x equal to 0.034. So that tells us that that's our concentration of hydronium because that's x, right? Okay, so that's our concentration of hydronium. All right, so strong bases. Strong bases, don't forget these guys, they're not the chemical opposite, as I mentioned in the very beginning. A lot of people, not just students, think that way, but it's not, they're their own thing. They're acting their own way. So yes, an acid and a base will interact with each other, but a base alone is defined as something that's going to take an H if it's Bronsted-Lowry, and if it's Arrhenius, it's giving up OH. So for an ionic base like NaOH, it's going to break up into sodium ion and a hydroxide ion. It's a stronger electrolyte. The more OHs you get in one step, they're breaking apart here. It's strong again if it dissociates 100%. And so we're going to look at the POH here and say that that is equal to the concentration of hydroxide. They're calculated the same way, so you really don't have to spend too much energy and time into memorizing POH versus pH. Just know that the POH has OH with it, and it's calculated the same way. All right, so a weak base is the same definition as a weak acid. It's not completely dissociating. Some of it remains together as a compound. And so the hydroxide ion concentration is very, very low. Finding the pH solution is similar to finding the pH of a weak acid. We've got to do an equilibrium. So that's where Kb comes in. So same thing as Ka. The larger the value here, the stronger the base. That's different from Ka, right? The procedure is exactly the same as what we did for Ka. Here's example 9. Determine the OH concentration and the pH for these two solutions. So we have part A, one solution, part B, another solution. We'll go through part A first. So since KOH is a strong base, it'll completely dissociate into potassium ions and hydroxide ions. The concentration of OH is the same as the given concentration of our chemical, our base, KOH. So we can make the statement that KOH is equal to this dissociation, which means the OH is equal to the KOH, we can say that the OH ion concentration is what was given, 0.225. So now we can use Kw, throw it in, solve algebraically for the hydronium ion concentration. And when we do that, we get 4.44 times 10 to the negative 14. That 4 is underlined because that's a significant digit. Then we're going to substitute the hydronium into the pH calculation. We're going to get pH. A part where you're going to have a possibility for making an error is if you stop here thinking that you're doing OH, get this value, which is really the hydronium, but think it's the OH and put this in like a POH, or stop where you're at this step, or just remember what, stay aware of what you're calculating. Okay, if you're asked to find pH, you've got to use the hydronium ion concentration. Okay, and so we plug that in and we get 13.35. So on the scale of 0 to 14, 13.35 is basic, right? So KOH is a base, so our pH that we calculated makes sense with what we were given. That's a good little check at the end that you can do. All right, B, this one's a stronger base. We have strontium hydroxide. And so 1 mole of strontium hydroxide is going to break apart. Look, it's got 2 hydroxides. So every time 1 strontium hydroxide dissociates, we're getting 2 hydroxide ions. So that's very strong. But we have to remember that when we calculate down here, we have a coefficient for that hydroxide ion. So the concentration of hydroxide is actually 2 times the concentration that was given in this problem. Let me go back. For part B, we were given the concentration of our whole base to be 0.0015. But because I have 2 hydroxides here, that concentration of hydroxide is going to be double. Here it is. So 0.0030 for our concentration of hydroxide ions. Then we're going to use Kw to figure out the hydronium ion. So we plug that in, and then we're going to substitute in the pH and get pH. We get 11.48. Now if we compare part A to part B is a greater number, so it's a stronger base. All right, we're almost done. So polyprotic. Poly is a prefix that means many, and protic means protons. So what about acids that have more than 1 H? Well, they get plucked off one at a time. So we would have the Ka1 being the first dissociation constant of the first hydrogen to come off, the most acidic, the furthest away, the most polar. That would be the H to come off first. Then the second H that would come off would be referred to as the Ka2. And then if we have a third proton in the molecule, then we'd have a Ka3. And you can see how they're related, the first one being the greatest value that comes off. And so for most pH problems, we use the first ionization. Okay, we look at H2SO4. There's 2 hydrogens there, so it will have a Ka1 and a Ka2. But the second ionization energy is going to be very small because it's really that first one that controls all the chemistry that it's going to react with. Okay? Well, let's take a look at this in action. So we have H2SO4, sulfuric acid. We dump it in some water, and this is what happens. It breaks apart. We get our hydronium. But then this sulfuric acid ion with just the 1 hydrogen now, that can interact with water again, and we can get another hydronium ion. That's the second dissociation because it split a second time. That first original molecule gave up 1 hydrogen and then a second. That second hydrogen, when it's lost, that's the second Ka. For most sulfuric acid solutions, the second ionization energy is significant and must be accounted for. How are you going to know when to account for it and when you don't? You'll be told in the problem, or by me. Okay. Oh, okay, so this is a picture that just shows it breaking apart in solution. And so Here we see a much bigger acid here, polyprotic. We have 2 hydrogens. Those are the ones that are acidic. The other ones are taken up by this carbon. So you can see I have 6 carbons, 6 hydrogens. So this is probably like a benzene ring, which is a 6-carbon ring structure with hydrogens coming off of each. And then we have some oxygens with hydrogens off of those. So the hydrogens that are connected to the oxygen are the ones that are going to be plucked off. Those are acidic. So how do we find the pH of an acid that has more than one proton? It's the same procedure, okay, that we've been doing. We're going to get X, which is the hydronium concentration, right? But what we're going to need to do at the end is we're going to need to multiply the hydronium ion concentration by how many original protons were in that molecule. So when we go through the ICE table and we get X, and we say, okay, that equals the hydronium ion concentration, that's from the first hydrogen coming off of the polyprotic acid. If there are 2, like for sulfuric acid, let's go back again, then when I do my ICE table and I figure out my hydronium ion concentration, I really multiply that by 2 to get the polyprotic, in this case, 2 hydrogen concentration for sulfuric acid. That's the difference. And it looks like that's the end of our chapter. So go ahead and try the homework assignments. You should see them directly relate to the examples that we've done here in the video, and we will see how you did in class. Bye.